Okay, so what I would like to do in this short 3-4 minute bit is to say a few words on kinetic energy. Now, kinetic energy is defined to be the total energy minus the rest energy. So this is the rest energy. It doesn't depend on the velocity or mass energy. This is the equal to mc squared, right? And like I said, it includes the mass energy of constituents plus the energy of interaction and kinetic energy of those constituents. So if you have an object resting on the table, it has a mass energy, and that mass energy comes not just from the masses of the constituents, but also from the energy, which includes kinetic and interaction energy between those constituents that contributes to the mass. So that's this part. So if you just explicitly write things down, you get an expression that looks like this. Okay. And what happens when you plot it? So here's U and here's K. Well, when U equals C, the denominator here is 0, 1 over 0 is infinity. So here's your light barrier. And so the whole expression is infinite, it diverges. On the other hand, at small u, well, what happens at small u? At small u, you have to do some Taylor expansions. When you do the Taylor expansions, you find that the whole expression reduces to the regular kinetic energy. So let me do the following. So here's the thing at small u, it follows a parabola, and here's your 1/2 mv squared, 1/2 m u squared parabola. And so it's the actual expression, what it does is, no, I'll just stick with the black marker. It follows this parabola and then falls off the parabola and it diverges. It diverges. Right, so what that means is that at u much less than c, kinetic energy better and better approximates 1/2 mu squared, which is a classical formula. And it's no wonder that humanity discovered that classical formula first, because no one thought about very large speeds or speeds comparable to speed of light, among other things. Otherwise, relativity would probably have been discovered earlier. There's one other effect that's visible through this graph. Those of you who followed the optional track will have learned that the reason it's not possible to transfer information faster than speed of light is because if it was possible, you could violate causality and the notion of cause and effect becomes meaningless. You can always find a frame in which you were born before your grandma. And in order, because that leads to nonsense, we conclude that it should not be possible to transfer information faster than light. So that was the optional part, and if you follow the optional track. And by consequence, it also implies that you cannot travel faster than light, because if you could, that you could transfer information faster than light. So that's in principle. In principle, why superluminal travel is impossible. But in practice, the mechanism that prevents things from crossing the speed of light barrier is this: that as objects of mass, that have mass, approach the speed of light, their kinetic energy increases more and more and more. And at the speed of light, their kinetic energy becomes infinite. Now, how do objects acquire kinetic energy? By someone doing work on them, right? If I want to accelerate the bicycle, I need to apply force and do work on that bike, i.e., I need to transfer energy into that bike. So this says that if you want to reach the speed of light, you have to transfer infinite amount of energy into that object. And even then, you will only approach the speed of light, not beyond that. There's a little bit more that you see as you approach the speed of light. You need more and more energy to achieve the same increase, or vice versa. If you keep adding equal amounts of energy, you will only gain less and less. So for example, let's say at this speed, your kinetic energy is 100 joules. And let's say this is 0.9 speed of light. At 0.99 speed of light, your kinetic energy will be like 1000 joules. And 0.999 speed of light, your kinetic energy will be 1 million joules or something like that. I'm just making up numbers. And so if you keep adding equal amounts of kinetic energy, you're going to get smaller and smaller payback. In economics, they have something called law of diminishing returns. It's not a physics law, it's just a term I'm borrowing from economics. So that's the situation. That's the mechanism that prevents particles from crossing, massive particles from crossing the speed of light barrier. In the second lecture on quantum mechanics, when we talk about Compton effect, I will go back to relativity for a little bit and discuss the notion of massless particles. One other thing that special relativity predicts is it predicts that it's possible to have massless particles, and that massless particles will always travel at the speed of light as seen by any reference frame. But for massive particles, this is the mechanism that prevents them from crossing the speed of light. We can also explore this theme from the force point of view. This is the energy point of view, kinetic energy point of view. We can also try to look at the angle, at a different angle from the point of view of forces. That's done in the third bit. And the upshot is that from the point of view of forces, if you keep applying a force, let's say a constant force, well, initially you accelerate, you have a constant acceleration. If you apply constant force, you get constant acceleration. So initially you're at small velocities, you're in the realm of classical physics, but then you get less and less payback. Your acceleration decreases, and then you keep applying force, but the particle just refuses to accelerate. When you reach almost the speed of light, you can keep applying forces that keeps increasing the energy. The kinetic energy keeps climbing, but the velocity does not. The velocity plateaus off, it asymptotes to the speed of light. So as you keep doing work, when you apply force, you keep doing work. As you keep doing work, keep pumping energy in. Yes, you do keep increasing the energy. The K keeps climbing, but velocity does not. So that's explored in the third bit. And you have one homework problem about that. And that's about it. Okay, so please watch the third part.